Hala, you can take your video down for this part. We'll get started in just a moment. All right, good afternoon, everyone. We will give people a few minutes to join and then we'll get started. All right, I've got 12:02, so we'll go ahead and get started. Good afternoon, everyone, and welcome to the third session of AI Virginia's Building Reuse and Decarbonization webinar series, presented by AI Virginia's HRC and VA Code. My name is Delaney Ogden. I'm the Director of Education for AI Virginia, and I'll be the host helping with the presenting the webinar. A few housekeeping items before we get started. You can engage on the chat feature with others today, so please use that. Feel free to tell people your name, where you're, calling in from, what firm you're with, and company. We will also have the Q&A tool available to use for any questions you might have during the presentation. So please use that tool when we get to the Q&A portion. And then if you have any connection challenges while you're on the webinar today, just remember to remain on Zoom. Zoom does a really great job of getting you reconnected automatically. So, and for optimum bandwidth, just make sure any background applications and windows are closed. After the webinar today, I will be sending you a survey. We would love to hear your feedback about the session. So please complete that when you see that come through. This session today has been approved for 1.5 LUs, and the credits will be reported within 10 business days after the session. And as I mentioned, we'll have a short Q&A period after the presentation today. Now I'd like to turn it over to Katie Irwin for a few comments about our webinar series. Katie?
Great. Thank you, Delaney. I'm Katie Irwin. I'm the chair of the A Virginia Historic Resources Committee. We meet monthly and welcome any and all new members to join us. So this webinar series evolved as a partnership between the HRC and the COAT committees. And we have four parts to it. This is the third one. And through all these webinars, we are showcasing the overlaps between historic preservation and sustainability to help reduce our carbon footprint. In 2 weeks, we will have the fourth and last in the series called Carbon Counts, quantifying the value of existing building stewardship. And we hope to see you all there. And please do share out this webinar series to your networks. Thank you.
All right, William, if you'd like to come on and do introductions.
Sure. And good morning, good afternoon, everyone. I'm William Abrahamson, co-chair of the AA Virginia Code Committee. Anyone who's interested in joining the Code Committee and spreading the conversation and activism in code, please reach out. There's info on the AA Virginia website. Our guests today are Hala Abadaf and Todd Steffens, um, both from Loring Consulting. Hala is the managing principal at their DC office, starting in electrical engineering. She has been integral to their company's work, enhancing uh, historic renovations and conservation. Todd Steffens is the vice president in charge of energy auditing, commissioning, and mechanical systems. He's a registered professional engineer in Maryland and New York, and a certified energy auditor and certified building commissioning professional. And we are looking forward to the conversation with them today. Please list any comments and questions in the Q&A box, and we will collect them and have a moderated discussion at the end of the presentation.
Great. Thank you, William. Hala? Think you're on mute. Oh, there you
All
go.
right, here we go. Good afternoon, everyone, and thank you, William, for the introductions. I'm just going to get started with our presentation today. Let me just go ahead and share my screen. Our presentation today is electrification and decarbonization strategies for historic properties. Historic properties is something that's near and dear to my heart. This is something that I've done quite a bit of work in. And I'm sure a lot of you are familiar with decarbonization strategies for, for new builds, for even existing buildings. But with historic properties, it's a little bit more nuanced. And I hope that this presentation today would offer you shed some light on what we look for as engineers within historic properties, and we're talking electrification. Learning objectives, you're looking at the learning objectives on the screen, but in essence, we would like for this presentation, the takeaways to be understanding of a larger carbon master plan sort of required for historic properties requires early investigation, things that we need to look out for. There are various system options that we're going to talk about as well. We're going to talk about energy auditing and benchmarking and sort of understanding the energy profile for the building for historic properties in particular. But we're also going to be talking about what happens after we architects and our engineers are done with a modernization project, which is how does the building owner continue to maintain a certain carbon footprint that we wanted to establish, but also continue to optimize it? Things fail, but we want to, obviously continue to improve and optimize. So what is decarbonization? And for decarbonization or electrification basically means replacing technologies that use fossil fuels as an energy source to provide energy within your building with an electrified source. But it doesn't just, kind of, it's not that simple. I think when we look at it, we always look at it into sort of three buckets. There is always the energy sources, sort of this middle of the slide area that looks at energy sources, whether they're fossil fuels that we're trying to get away from or on-site renewable energy. But the kind of the other buckets that you want to think about is optimization of your energy, optimization of envelope, which we typically deal with regularly on in terms of an MEP system in response to a modernization strategy. How do we do system upgrades? How do we optimize our energy end uses within the building? And then the third component is something that's also near and dear to our heart, which is operation and maintenance. We typically get involved after a project is completed with making sure that what we design actually works within a historic project. And Todd is going to talk to you a little bit about that. as well. A lot of the examples that we're going to be talking about today come out of our recent projects, a very recent successful project for us, the Michigan State Capital Infrastructure Upgrades. This is a job that was completed in 2022, and I think it offers an electrified solution for the building, but also includes a lot of the energy optimization solutions that we're going to be talking about and showcasing for you today. We always talk about a listening tour, and a listening tour has to always start with understanding where energy goes in the building and the EUI for the building. And with that, Todd, I'm going to turn that over to you to talk a little bit about ASHRAE audits and retrocommissioning.
Yep. Yeah. So just to define some terms, an EUI is the energy use intensity that is in a building, and it's measured in one of two ways. There's a site EUI, which is essentially what your building's utility meters are reading, and you get an electric bill or a gas bill or a water bill for that each month. There's also a concept of source EUI, and a source EUI is how much energy does it take if you consider what the utility company is having to generate to get you your electricity or to deliver gas to your building. So this energy metric is a really good gauge to both understand how well your building is currently performing and how well it's performing compared to other buildings in a national database. And the EPA and Department of Energy actually collect this data nationwide on a periodic basis. And it's the metric that forms the basis for the Energy Star labels for buildings as well as for other campuses and facilities. One way to understand a building's EUI, if you're looking at it just from a utility meter perspective, that it's a very coarse tool to look at, because all you're seeing is a look back for about 1 month periods of what the whole building was doing. But in order to understand exactly why that utility reading is occurring, you'll need to either do an energy audit or a retrocommissioning task. And these are fairly similar from an outside perspective, but there are different objectives to each of these tasks. So an energy audit is, as defined by ASHRAE, can be in different levels of intensity. So they'll define a level 1, 2, or 3 energy audit. And that's in order of increasing complexity. So a level 1 audit is what you would do if you walked through a building, you didn't do too many actual tests on the building systems, and you were able to just catalog and estimate where the energy is going, say to the lighting system or to a building boiler. Level 2 and 3 get more intense with their financial calculations, where you have to put in more detailed cost information as well as more complex energy models that are going to predict what a given energy conservation measure will save. Energy audit is always looking for opportunities to optimize the building's energy use. Retrocommissioning is a similar process, but instead of only looking for energy savings, you're also looking for parts of the systems that may not be functioning properly to begin with. A retrocommissioning measure does not necessarily have to result in an energy reduction. For example, if an exhaust fan is broken and offline, and one of the retrocommissioning measures to suggest how to fix that is you have to repair the belt on this fan. That's going to increase the energy use in the building. However, now the building is going to function as originally intended. Next slide. So what do we do with this information? One thing we're doing is breaking out, like I said, the energy use to the energy being consumed to its end uses. This is a pie chart that would come out of an energy model following an ASHRAE level 2 or 3 energy audit. And these are useful so we can see what parts of the building are best to be attacked for energy reduction purposes. So in this example, the space heating and air distribution and cooling are most of this building's energy use. So those are the 3 areas where we would start looking at in order to have an idea of where we're going to attack to reduce energy with our energy conservation measures. Things like, you'll notice that small purple sliver with domestic hot water is only 1% of the building's total energy use. So even if you got a 50% reduction in that end use, you're really not going to impact the overall kBTUs that your building is consuming on an annual basis. So this is a good way to prioritize what we're looking at in our ECMs. And we can convert that energy use directly into carbon emissions. So we had mentioned site versus source EUI in the previous slide. The utility company, even if you have a fully electrified building, it does not necessarily mean you have a net zero emission building, because depending on the mix of the fuel at the utility end, they have to burn the natural gas at their plant to run a generator instead of you burning it on site. And that actually is less efficient of a system to deliver it as on-site combustion, but there are other advantages to it. Next slide. And then, yeah, just a word about the building energy and controls and how that's related. The buildings are operated at their head end by a computerized system. This system takes into account incoming signals from your various HVAC, electrical, and plumbing systems, and it converts them into a user interface at a head-end computer. So in this example, we can see is an air handler, and it's pulling points in. Each of those individual blocks is a different input or output point. And we would think of an input point as what a temperature sensor is telling the computer, and an output point as the computer telling the machine to do either one action or another, turn a fan on, modulate a cooling or a heating valve, things like that. And it's important to both have that and make sure it's reliable. And that's one thing a retro commissioning process can do, is when you go into an existing building, look at the actual points in the field versus what you're seeing on your head-end computer. So this photo on the left is part of a retro commissioning project we did, where this is a chilled water flow meter. It's a turbine type, but you can see that it is turned a little bit at an angle to the pipe. And this type of sensor needs to be installed in perfectly parallel to the pipe to get a good reading, because then the paddle sensor inside the pipe is actually perpendicular to the direction of flow. So we could still be getting an input signal from a device like this, but when we go to look at it on the computer, the value that it's outputting will not be correct. So it would be relying on unreliable data point. So identifying things like this are key to understanding the initial starting conditions for your building.
Yeah, thanks, Todd. And a lot of historic properties, in addition to controls, obviously, that Todd is very good at, sort of has a trained eye to pick up. A lot of the retro commissioning recommendations would result in what we call low-hanging fruits. These are things that could be fixed easily to have the building better perform. But with historic buildings, the thing that we spend a lot of time on is ventilation. And how do we provide proper code required ventilation quantities and quality into a historic structure that many times was not even designed to allow for ventilation, or doesn't have ventilation properly at the moment. And in the case of the Michigan State Capitol, their ventilation systems are things that we're probably very familiar with. You're probably seeing a lot of these ventilation strategies around the DMV area, where you have on-grade areaways that are providing you with outdoor pathways for outdoor air to come into your buildings. The problem with this is, in terms of air quality, is that if you've got, for example, in the case of Michigan, if you've got a snow condition, then you have to make sure all of these grates are clear of snow. So that requires a lot more maintenance upfront work. But in the case of Michigan State Capitol, these areaways were on grade were also trapping sewer gases. The vent pipes that were kind of passing by were also contaminating air pathways that are being delivered to the building. And in addition to all of that, it was presenting a security risk for the building in terms of somebody who wants to come in and tamper with the quality of air for the capital. These areaways were delivering outdoor air to a zone of the building. I would call it ground floor, ground and first floors. But upper levels of the building were provided with outdoor ventilation, which wasn't sufficient through these very thin slots. And I don't know if you can see it through, but the decorative elements right here in the facade include two thin slots that historically, and that's how they were designed, is to provide ventilation through the facade, through the envelope, into the building. And on the other side of this decorative element, that's where you have your fan coil unit. Again, that was a strategy. That was how the building was designed, but it wasn't necessarily optimum. It was providing unfiltered air into the spaces, and the fan coil unit had to work hard to actually condition the air that was coming into the cavity of the fan coil unit through these air slots. So this is a picture of the other side of that decorative element, and you're seeing the fan coil units and the enclosures that we had to deal with. And part of our listening tour is understanding what we could do with the fan coil units and how we provide ventilation into these spaces. And I would say this is something that's common to a lot of historic properties. You have ventilation, the minimum ventilation, or sometimes no ventilation that comes in from central sources, but you are having ventilation to come in through the facade. And then you've got perimeter units that are doing your envelope conditioning. And it's very important in a historic property, if you're thinking about a modernization, to really understand the cavities that we're working with. If you're going through an electrification strategy that uses, let's say, a heat pump, typically or most often, these are going to move away from the 180-degree class systems, temperature water, heating hot water systems, to 140 degrees or sometimes 130 degrees or even lower. And what that means is now all of a sudden the coil that you had or the radiator that was housed within these enclosures, once you go to a larger coil to accommodate, you'd have to go to a larger coil to accommodate a lower temperature. Well, what does that mean for historic property? That means part of this listening tour has to look at the feasibility of upgrading these terminal units, whether radiators or fan coil units. You got to think about that very early on as you are trying to implement a modernization strategy, but also as you think about system selection. So when it comes to systems, the two I'm going to talk about, which are very popular with whenever we're talking about electrification, is heat pumps and VRF systems. And with heat pumps, these are systems that use water as a medium for regulating temperatures within the building and also exchanging heat with the outside world. There is what you're looking here is a graphic for an air-water heat pump, and what it means is your exchange medium with the outside is through air, through an air cycle. And in the summertime, you're probably very familiar with how that works, which is based on the heat pumps that you'd have in your house. In the summertime, the compressor is working to provide chilled water or cold water within this side of the HVAC cycle to provide you the cooling that you would need within your spaces, and then it would extract the heat from your spaces and then deliver it through this cycle to the outside world. In the wintertime, the compressor works in reverse. It sort of reverses that cycle. But what the compressor is trying to do is to chill the water through the cycle that's in touch with the outdoor conditions. And even in outdoor conditions that's at 40 38 degrees, you're able to have a gradient between the outdoor air conditions and then the conditions or the temperatures within the cycle to allow you to extract heat from the outside and then deliver that to your spaces. For larger commercial applications, you would have a heat pump solution that would also could be coupled to an air handling unit, or could be coupled to an outdoor air a DOAS system, and exhaust systems. And the refrigeration cycle on the inside of the building is still the same as a heat pump, or on the slides that I showed before. But then on the exterior, or sort of the other side of the slide that's in touch with the outside world, it is not air. You're in contact with another water medium, and that's typically through a cooling tower. And this system works really well for large applications. The caveat here is that in very cold weather climates, the outdoor conditions might become very cold, that a heat pump solution is not able to really create that differential or temperature gradient with the outside conditions. And that's where we come in and add another source of hot water to be pumped into the building, or supplement or boost the cycle. And this is often done through a hot water boiler, that, again, that we're trying to walk away from, and in a decarbonization strategy. VRF systems are also becoming very popular with historic buildings, and that is because instead of water, you are using a refrigerant that is a much better medium in terms of exchanging energy, or as an energy carrier for within your building. And these refrigerants are use typically a much smaller pipe than a pipe that you would use for a water-based system for a heat pump, which is something that's really appealing for historic properties, because then you're not as intrusive with these pipes within the historic property. The other types of VRF systems, or variable refrigerant flow systems, is a system that is sort of a hybrid solution, offers a hybrid solution that provides refrigeration through a refrigerant-based system between the outdoor unit and then what we call a controller or collector box. And then it uses traditional water-based systems to all of your indoor units. This is something that you could use, for example, if the owner does not want to invest in wholesale modifications and they already have a water-based system. But also, we at times have used this system where you have limitations on where you're using refrigerants within the building. Refrigerants, again, as I mentioned, these are great medium, or great material for exchanging heat, or for exchanging energy within your building and transferring energy within your building. But they do come with the sort of the penalty of having a global warming potential, something that would be, we if you're doing an electrification program, that you want to pay close attention to, because it's also carbon that's impacting the ozone and impacting the environment. So a very popular refrigerant that you're probably seeing being phased out, or your engineers are telling you this being phased out, is R410. This doesn't take place right away, but it is being phased out because of the score, the global warming potential score that it would offer, although it has a lot very low flammability concerns. The manufacturers are starting to use different kinds of refrigerants that have a wide range of global warming potential factors and flammability concerns. But where this comes into play with historic properties is, if you're trying to use these alternate types of refrigerants, they are more flammable, which means that you have to provide proper isolation. You're not going to be able to take that refrigerant throughout your building because what if that refrigerant, excuse me, were to leak? Then you would have a hazard in addition to a hazard to air quality, in addition to flammability concerns. So a lot of times these alternate forms of refrigerants, they require a lot of calculations. They require isolation. You could be seeing a lot more dampers that have to get introduced within your historic fabric. They, at times, on the more extreme sort of consequence of this, it could be specialty exhaust and ventilation systems, just to mitigate the impact of these refrigerants, or the risk for refrigerant leak within the building. So I wanted to spend some time to talk about Michigan State Capitol. Again, this is a job that's near and dear to my heart. It was completed, we started this job in 2016, it was completed in 2022, and it provides for and it provided for a complete infrastructure upgrade at the Michigan State Capitol, but it also allowed for an expansion to the Michigan State Capitol for providing a visitor center. So when we were designing this infrastructure upgrade, we wanted to make sure that the visitor center, Heritage Hall, as designed by Quinn Evans, is also integrated into the holistic energy master plan and carbon master plan that we're trying to work through with this historic capital. When we sort of got started the job, we had to obviously go through the listening tour, understand how energy was being used, and Todd has spent a lot of time in the basements trying to understand where the control deficiencies are. The building was using an energy source for heating the building that was coming from a district energy provider. It was steam that was generated from a plant remote from the site, and then it was serving a lot, not just this capital, but also other buildings on site. And the issue with steam systems is that they're typically not as energy efficient as a kind of modern heating sources that you could have on site, but also had reliability concerns. The capital had reliability concerns in terms of regulating that temperature. It requires a heat exchanger. Sometimes, there were issues about condensate, and returning that condensate to the district energy plant. The capital was also in the summertime, it was cooled through on-site chiller. And just like what we talked about with the refrigeration cycle, you've got that compressor heat that has to be released to the atmosphere. And the way they've done it was releasing it to the atmosphere through this evaporative cooler that was sort of hidden in an areaway below grade. And this is a graded areaway, and in shoulder seasons, at times you would see a plume of condensation, basically, or a plume of vapor that would be carrying chemicals and predominantly water that would be pluming out of this area. When we looked at this, it wasn't we couldn't, fathom a solution that would involve a cooling tower. Where would you put that cooling tower? You have to kind of think about, the historic context of the site. But we also looked at this as an opportunity. The original sort of master plan for the capital, or as the original architect of the capital, Elijah Myers, he had envisioned a capital that had the main entrance off of the east lawn, and you're seeing the east lawn here is very well maintained and landscape, but the west lawn, what he had not envisioned a surface parking lot. He had envisioned a landscape solution for the west lawn that wasn't, definitely wasn't a surface parking lot. So our geothermal system, I'm getting ahead of myself. And so the system that we came up with was a geothermal exchange system that was sitting on the west lawn of the Capitol, 273 wells, 500 feet deep, and that was coupled to a central utility plant, coupled to a chiller heater equipment, and then running hydronics from that central utility plant into the various zones within the building to heat it and cool it. This well field that we took advantage of on the west lawn of the Capitol provides 100% of the heating and the cooling demands of the Capitol. And we walked, as a matter of fact, in 2022, as we were closing out the project, we walked through the central utility plant and walked through the Capitol on a very cold January morning. And the building was, completely heated and cooled by the geothermal system. It did not, the gas boiler that we had put in, which was used for taking care of the snow melting load, that does not kick in, was never designed designed to kick in unless you have temperatures and loads that would call for it. And I'm hearing from the capital that that boiler has yet to kick in, but we've got it there as redundancy as well. But what that did was it allowed the vision of of Elijah Meyer to come to fruition in terms of a landscape solution that we definitely didn't take care of as MEP engineers, but that was part of the project as well. Whenever we talk about an electrification solution, you always want to think about the electrical system and the capacity of the electrical service. But you always, the sort of the knee-jerk reaction is, well, we need to upgrade the electrical service, and that's not the case necessarily. You're looking at two charts here from buildings that we had looked at for an electrification solution. And on the chart on the left right here is a cooling season dominant building. And yes, they were using a gas boiler here in the winter months to heat their building. But if we were offering an electrification solution to the fossil fuels that they were burning through the winter months, these bars would come up to this threshold. It might not get to the purple line where you've got your capacity. So this may be a situation where you don't have to upgrade the electrical capacity. We also looked at a different building where their profile was what we call all-season load profile, where they've got a load that's consistent within the building that is year-round. And in this case, if you just change your heating sources, the fossil fuel generated heating sources in your building to an electrical generator or electrical heating sources, then yes, you would be exceeding that capacity. But what we were able to do is to talk to the owner about, coupling this electrification solution with other types of energy conservation measures, VFDs on the fan systems, lighting control strategies, going with a more energy efficient lighting systems within the building. So these could potentially reduce all of these blue bars down and at the same time allow you to change the heating system within your building without having to reach capacity. So it's a delicate study that we electrical engineers have to look at when in working with mechanical engineers as well. Lighting upgrades, I call that a sort of the no-brainer. Everybody should be having LEDs by now, but I think you get a lot more bang for your buck when you're coupling that lighting upgrade or the lamp replacement with a lighting control solution that offers sort of automatic features that are either occupancy based or schedule based. Historic buildings are well known to have good lighting to come in from windows. It could be, in the case of Michigan State Capitol, they also had skylights. Integrating daylight daylight into your lighting strategy is also a very effective tool that would help reduce your carbon footprint and you're optimizing your energy. Whenever however, you're dealing with lighting controls, you want to think about a historic structure that's heavy, that's got a very thick masonry. And if you're putting in control systems, are you going to channel the walls to make them wired, or would you go with a wireless solution? Particularly for historic structures, whenever you want to think about a wireless strategy, you want to think about putting in or doing a Wi-Fi coverage study to understand what you can do and what you can't. Plumbing systems, also they use fossil fuels to generate domestic hot water. There are alternates that would provide you an electrification solution that could be, for example, a small tankless water heater that could take care of your small restrooms or your bathroom loads. But for the larger systems and for the larger sort of prep kitchens or the pantries, you could think about an air-cooled heat pump solution, similar to what you would do for HVAC systems. On-site opportunities for on-site generation. If you're talking to any historic preservation architect, they'll tell you there's no way we want to see this on the roof of our building. But that doesn't have to be the case. There are opportunities to conceal PV systems. These are the solar panels that a lot of us are familiar with. But I would I think what we've done also is to examine integrated photovoltaics as a solution to generating on on-site energy through photovoltaics. This is a study, pictures of a study that we had done recently for the Michigan State Capitol, who have great opportunities for integrated photovoltaics into their skylights. The yield off of these systems is definitely smaller than what you would get off of a PV panel, but they're coming, they're coming around, and technology, I think, is continuing to improve these types of systems. Oftentimes, whenever we're talking about modernization for an existing building, and specifically for a historic building, you got to have an understanding of the treatment zones or the historic preservation zones within the building. These are things that we as MEP engineers work very closely with a historic preservation architect to understand where are the go, no-go areas within the building. The Michigan State Capitol, the areas identified in purples were zone 1, where these are the areas of the building that had a lot of rich historic fabric that we couldn't just put a new chase in, or we couldn't channel walls without a lot of thought and attention to that. But what we do on the other side of this is, after we understand where the historic preservation zones are, we go in and try to understand how do the hydronic zones within the building overlay with historic preservation zones? How does air system get distributed in air zones within the building, and electrical zones within the building? How are those arranged to overlay with your historic preservation zones? And at times, these would influence the implementation or actual construction. So take the case of the fourth floor had the Senate chambers. These are large assembly spaces that, at one point we were talking about doing the entire fourth floor. But when we looked at hydronic zones, we noticed that the hydronics for this area of the building are all connected with the third and the second floor, but that wasn't necessarily the case for air systems. And that wasn't necessarily the case for electrical systems. And these are areas, and this is a building that had to be maintained in operation during construction. So this definitely came in handy as we were thinking about an implementation strategy. And I can't talk about an implementation strategy without putting my contractor hat and thinking about constructability. And I have always been an advocate for designing in place. Take the full team with you to the site and try to have the discussion, in these kind of monumental spaces. Where are we putting the thermostats? What are we doing to the lights? We're going to have the thermostat and the lighting control station at the same time, at the same location together, or there are opportunities to optimize. I think seeing is doing it in places sort of, you get a lot more, obviously a lot more collaborative, but I think a lot more, it makes you a lot more in tune with the solutions that you're providing. And lastly, I always say that when you're working with historic properties that will be there for much longer than a lot of us, hopefully on this call, you want to think about future modernization projects. Are there opportunities to put in future pathways? Are there, the most successful modernization project is the one that you make successful for the next engineer that would come from, in 10, 15, 20 years. And now I'm going to turn it to Todd to talk about, after we finish all of our modernization and our projects, how do you maintain your carbon footprint within the building?
Yep. Thanks, Hala. Yeah, so operations and maintenance, I broke it down into 4 categories here. The main goal of this, like Hala said, we've just gone through a large capital improvement project, we're assuming. And how do we make sure that the savings that we projected during the planning process and the construction are persistent over time? Because it's a lot of money. These things drift out of calibration and they get wear and tear. And there's ways that we can go about identifying where that's happening and also minimizing it. So the first and most obvious would be just a regular preventative maintenance program. And this is really a standard practice, but you'd be surprised how often we go into buildings doing energy auditing and retro commissioning, where we actually find that they have what we call like a run till death preventative maintenance program where they just turn these things on, let them run automatic, and rarely come back to actually service them. And in historic buildings, this tends to be the case a lot, especially if we're getting into a modernization program and a decarbonization program where the building operators may not be as familiar with the new equipment. So in this example, we've got a couple pictures from some old buildings that we did studies in. A lot of it is things that seem simple but just can get overlooked. So on the left-hand side is a cooling coil inside of an air handler, and you can see like a cross-hatch pattern on there, like the big X's. Those are actually areas where the existing building filters had degraded around the edges over a period of what we presumed was 15 years without being changed. And those dark areas are where dust actually circumvented around where the original filter frame was, attached itself to the cooling coil, and then cooling coils, because they get wet, and if they get wet coils with dust on them and then it dries out later, now it's caked on dust onto these cooling coils. And it just reduces the heat transfer efficiency. So now you're using more energy to have the same effect just because we weren't closely monitoring these, our filter change schedule. Filter changes can also, especially since Hala was bringing up VRF and refrigerant systems, if your filters on those systems on the evaporator coil start getting clogged up, you can lead to other maintenance problems like icing up of the DX coils. As your filter loads up with more and more dust, it actually restricts airflow more and more and becomes a more efficient filter. However, in a refrigerant system, if you're not getting the expected airflow across the coil, you start developing ice buildup, and then you can actually develop a dam of ice in your HVAC unit, and it will shut the unit off, and then you'll have to come investigate why. And oftentimes it's because of filtration problems like this. Next slide. Measurement and verification. We had mentioned earlier about EUI. So a measurement and verification program in a building would be intended to, on a quarterly and annual basis, make sure that we're measuring the total energy use of the building and that that's in line with what was predicted during the initial design and construction. In order to do that, you need to have designed meters in place that are usable. So on the far right is just a bank of electric meters serving a condo building we did a survey for. So the metering can either be one single incoming electric meter or multiple electric meters. And when you get into buildings that have multiple electric services and end users, it could be a complex task just to keep all of those meters straight. We're also on the left are two examples of both of these are steam meters. The one on the left is a modern Onicon digital meter that's measuring both how many pounds per hour we're currently running through a system, and then it will totalize that over a period of time and report it to a utility. The rusty looking dial one next to it, that's also from that Michigan State Capitol building. Hala mentioned they were getting district steam from the Power and Light Company. And this is the device that they have on hand to actually meter that. And it's not digital. You have to go in and actually physically read the meter. But making sure that you're actually tallying these and analyzing it on a regular basis is one of those points of training where the building operators and management really need to be educated in why are we doing this M&V process and what connotates success and what connotates a need for alarm and correction. And next slide. So if the M&V is giving us a big holistic view of the building, looking at just what your meters are saying, the building automation system is the computerized tool that we can use to drill down if there is an issue and start determining where might we be having problems. So this is a screenshot from the Michigan State Capitol building's main chiller that was operating prior to our prior to our project to modernize the building. And this is just like a whole data stream where we're taking those individual points out in the system that are being monitored, say chilled water temperature, pump speed, anything else that's going to be related to energy consumption, and watching how that is functioning over a period of time. We can see this is about 3 weeks worth of data from a single chiller in that plant, where we're able to see and track how well this individual piece of equipment is running. And there can be hundreds of pieces of equipment in a building. Each of them are going to have its own separate trend. And that's another area where it's important for the building operators to be able to understand what they're looking for when they see this, and what actions they would subsequently need to take if they see something in their analysis that appears to be an error or out of calibration range, or something where it's possibly going wrong, where they're expecting a value to be X and it's actually Y. And they're going to have to go out and into the field and troubleshoot that. But knowing where to start is at this building automation system level. In addition to just simply looking at potential problem areas, you can also look for areas where you can improve and smooth out the system that will place less stress on the equipment, and therefore extend both the efficiency and the lifespan of that equipment. When we do these studies, oftentimes our life cycle cost analysis is going to be on a 25-year period. And that's picked primarily because that's a common manufacturer's lifespan for a given piece of HVAC or electrical equipment. But over that period of time, you can make sure that you maintain efficiency at a higher level than if you were not to have this operations and maintenance program. So this is an example of a study we did at a data center that was put into a historic courts building in DC. And that blue trend line represents the temperature profile in the room prior to any corrective actions being taken. You can see there's big spikes and troughs in that trend line. Each of those is going to impose stress on the operation of the system. So every time you see the trend line drop, that's the temperature dropping because the compressor kicked on. And then it maintains for a while, then it spikes up and then drops again. And every time that drop happens in this trend period is added stress on the compressors for the system, because it's going on and off and on and off. So what we want to see is, after we made our recommendations, this red trend line, which is a little more smoothed out, and it's going to be less stressful on the equipment and allow it to operate, maintaining the same general temperature set points over a longer life cycle. So you extend the life cycle to the extent possible. Next one. And this is an example of an independent trend that we had set up in a laboratory building, where we had to maintain pressurization in this particular lab, even through a power outage. And what we noticed when we had this data logger set up during a power outage is that that system wasn't functioning properly. So in addition to the energy considerations that you're going to have to be looking at on this equipment, part of what we mentioned earlier with the retro commissioning is the system functioning the way it was designed to be intended to function? You can see at that trough point where the trend line bottoms out to 0, that's indicating that this room did not maintain a differential pressure across this power outage that we had simulated. So trying to figure out why that is like an error point. So the building operating engineers will be able to read a trend like this and then understand, okay, there was a problem in the system. We need to either ourselves troubleshoot it or then reach out to outside help in order to help troubleshoot and see why the system is behaving this way. Testing, adjusting, and balancing is critical to making sure that you have the correct flow rates in a space. So just because on the design drawing, when we design a new HVAC system, say, we call for a certain amount of airflow CFM or water flow gallons per minute, we want to make sure that what the system is seeing, that BAS system that the building engineers are relying on, is actually happening. So this is an example of a recent project that we were working on where we had designed a new HVAC system, and these are offices, and they're all south-facing offices. But in this case, we had designed for this institute director office 2 linear diffusers with 170 CFM each for a 340 CFM total. And that was what was on the design. That's what the contractor submitted to us in their balancing report. But they were still having temperature complaints in these spaces after they had moved in. So we were able to go out and then measure what the airflow is at those linear diffusers, while at the same time looking at what the BAS was reporting. So the set points for this system were that it was supposed to provide 340 CFM. The BAS was saying that it was supplying 340 CFM, but when I put my duct airflow hood on top of it, we were only getting a little over 200 CFM actually delivered to those diffusers. And the reason is, on the picture on the far right, you can see that's the VAV serving the space, that there's an inlet sensor on those VAVs that is reporting that CFM value back out to the BAS. And having not done a proper balancing process during construction, we were able to identify that they're getting temperature complaints because their airflow was deficient, even though the BAS was not flashing any alarms. They needed to calibrate that box properly in order for you to get usable, good data out of the BAS. But in this case, we've come around, and this is more common practice in laboratory buildings and healthcare buildings, but we're starting to recommend a regular period of testing, adjusting, and balancing in a building so that we're able to make sure that these things, which do drift out of calibration, maintain that calibration through the life of the equipment. Next one. And just another example of where the BAS and the actual balance of the system can be a little bit deceiving is this is yet another shot from the Michigan State Capitol building. This is a hot water system that's dedicated to a under slab snow melt system that is on the walkways leading up to and around the Michigan State Capitol. And this shot on the left is a screenshot of their BAS system, where they're showing pumps active to circulate the hot water through the circuits. They have 3 different zones of controls because they have 3 different zones for the snow melting system. And they're measuring the temperature of the water going into each zone, and then the temperature of the water coming out of each zone. But we were noticing that there was still some ice buildup in what seemed to be patches out on the sidewalks and walkways. And we're trying to troubleshoot as why this might be, because we were looking at the flow rate for the system looked good. The temperatures going in and coming out looked like what we expected them to be. When we go to physically actually inspect that system on the right-hand picture, you can see there's 2 small metal boxes on the far right-hand side of that photo. And those are the temperature sensors that are represented on one of these circuits. And we identified which pipe header was having the problem spots out in the snow melt walkways. And looking at these sensors, what you'll notice is each one of those orange pipes is a separate independent circuit from the main header circuit. So each of those has to have proper water flow as well. So we were getting the appropriate aggregate temperature at the sensors, but there was a single circuit from that header that was actually deficient on flow. And I'll let you go to the next slide.
I think Todd, we're missing a slide, but yeah, that was the last slide where they had the graphical.
Would be a thermographic image, so it's an infrared image, and we could tell because it lights up just in colors. One of those circuits was actually just blocked completely, and it was getting 0 flow, and that's why they had patches outside that were.
Yeah, I'm trying to pull it up, but yeah.
Yeah, that's why they had patches outside. So we had to bring in the balancer just to check each of the circuits independently from the main header flow rate sensors.
Yeah, this is the image, right?
Yeah, so you can see the circuits that were working properly are lit up bright white and red. But this one where in the crosshairs is a circuit that is stone cold. It's at the bottom end of that temperature gradient. So that's not getting sufficient flow. And the balancer came in and was able to make sure that we got not only sufficient flow in that one circuit, but in all of the circuits to keep it balanced.
All right. So I think that brings us to the end of our presentations. I thank you all for the opportunity to come here and talk to you about electrification or decarbonization solutions from an MEP perspective. And Todd and I are going to stick around to answer any questions you may have. Delaney, I'm going to turn this back to you.
Thanks, Hala. I'm actually going to turn it over to William as the moderator. William?
Yes, well, thank you both for the great presentation. There was a lot of content there. Thank you very much. We did receive a couple comments coming from the Q&A, so I'll ask those first, and then I have a few other additional questions that I think people will be interested in. First question, what are the two projects on the right side of the PV slide? So I think you had the solar collector, thermal collector on the one side, and then two others on.
Yeah, so let me go navigate to where that is. These are actually pictures from actually a solution that we had looked at to implement at the Michigan State Capitol. It wasn't a project that we had done, but it was an integrated photovoltaic. I'm going to share my screen here in a bit just to get you all oriented, but it was an integrated photovoltaic solution that that we found that we were talking to the Michigan State Capitol about implementing at the Michigan State Capitol. So it was basically coming in from the manufacturer. It wasn't a specific project that we had done. But you can see here, let me go back to that picture, but you can see that the picture, what was appealing about that picture is that it offered an integrated photovoltaic solution. And these are, integrated photovoltaics, they come in sort of different technologies. There is one where you're seeing these pixelated elements within the skylights. That is the photovoltaic element embedded within the skylight that was offering, generating the electricity. This is another form of integrated photovoltaic that relies on a thin film that would be sort of fitted on top of the existing skylights to generate electricity. Obviously, when it comes to yields, you get a lot better yield from a photovoltaic system. And then you get the next one would be these pixelated type integrated photovoltaics. And then the thin film would give you the lowest yield out of the three.
Okay.
So yeah, these were not necessarily our projects, but these were images that we found of products that we could potentially apply and study for the Michigan State Capitol.
Okay. Thank you. Next question is, sorry, I lost my window here. Now this is, what is the cost to do an energy audit or retro commissioning? I realize that's a big question. Every project's different, but how do you take initial steps to approaching conversations about cost with your clients?
Yeah, so typically a general range for an energy audit, and because there are the three levels, and the levels get more complex as you go. So an ASHRAE level 1 energy audit can be as little as 15 cents per square foot. And it really depends on what your goals are from a project. So some places, most of the places where we do ASHRAE level 1 energy audits that are the cheapest version, they're looking to just simply comply with a code requirement or something like that. The ASHRAE level 1 energy audit is really just to give you a rough starting point. Level 2s and 3s will get anywhere, it'll start getting more expensive, anywhere from like 30 cents a square foot, all the way up to $1.50, depending on the intensity. And those costs are directly related to just field survey time. So when we start working with a client who wants to do an energy audit, we start looking at what are you looking to do? Are you looking to just switch a few fans and air handlers out, or is this a large capital expenditure project that you're looking to get more detailed information? So a level 2 is going to have a lot more of the financial payback information. It can be either based on a professional cost estimator's opinions, or we have some historical examples in our database where we've worked on several hundred of these projects so far. So we have a good handle on some recent installation costs, but oftentimes we would recommend a professional independent cost estimator. And a level 3 gets even further into that, where we start having to do complicated financial payback calculations and life cycle cost analysis, which we're starting to get into that 25-year projected LCCA. So we know that we're going to do a major capital upgrade, or maybe even a new utility plant or something to serve a historic building or cluster of buildings. When we start getting into that level, it starts getting to those upper cost ranges of $1.50. And that would be typical for most historic structures and buildings. Things like laboratories and hospitals and healthcare, those start getting even more expensive than $1.50 a square foot, and maybe even up to $2.50 to $3 a square foot, depending on how complex that specialized facility is.
Okay. Taking off that, I think I'll put this question to both of you. Can you speak to the feedback loop, if you will, back to the carbon master plan or the energy master plan? Once you do the survey and you set your project goals, you've got a plan, you got your strategy. How often do you keep coming back to assess progress towards meeting those benchmarks that you set?
For like a measurement and verification program, the most common is to do quarterly visits.
Quarterly.
And it depends on what the owner was looking for. It can be for a period of 1 year or up to 5 years. Would be useful to have retain your energy auditor to do that M&V. When you're looking at those time periods, you'll start to be able to identify problems early on. So on a quarterly basis, if you come in for the first 3 months, say January through March of the year, what you're doing is you're comparing it back to the original energy and carbon projections and seeing what you might be expecting for that time period versus what you're actually seeing. And that's a process called a model calibration. So when you do that initial energy model, it's going to put out both that pie chart that predicts where's the end use systems that it's going to, but also give you a month by month projection of January. We expected 100 kBTU, and what we actually saw was 105. So could that be explained by the weather? Was it unusually cold this January? Or is there something deeper that we have to go back and look at for that hypothetical January, where we're saying, oh, we saw this pump operating 24/7. It's really supposed to only operate during occupied hours or 12 hours a day or whatever that particular point happened to be. But that's why it's important to have that measurement and verification built in to the BAS, so you have like a systemized way to go look at it. Usually when we're doing it for a 1 year post occupancy, quarterly checkups plus an annual, we're helping guide the building operators through that process. And then we're giving them the tools to be able to do it going forward after that, because that's usually the most cost effective for the owners.
Okay, thank you. Going back to Hala, one of the most interesting things for me in this discussion was where you were speaking to the balancing the historic preservation zones. As an architect, also evaluating against IBC alteration levels, and especially of differing levels of disturbance around a building. And one of the classic fails between architecture and MEP coordination is, where's the access panels? And the MEP assumes everybody knows there's an access panel here, and the architect doesn't always know that. Especially could you speak a little bit to how you have that discussions, especially moving from centralized to maybe decentralized systems like a VRF?
Yeah, so I think that's a discussion. Actually, I'm an advocate for having the access panel discussion as early as possible because at times it may influence ceiling decisions or sort of what we do within a space. In a historic structure, especially the prominent ones, the sort of the highly decorative spaces that I had a picture of where, I talk about designing in place. That's a great opportunity to talk about what do we do with this access panel and where do we put the thermostat or the T-stats. I think this just comes down to having a lot higher sensitivity by the engineer, to be honest with you. I think a lot of engineers just pass the can and they don't have the access panel discussion very early on. But I think it's having the sensitivity to understanding where these access panels need to go. And yes, they need to be coordinated in field, but you got to think about it up front. Sometimes it may influence how your ceiling would look and also design decisions about what the ceiling would look like. It could be a different type of ceiling that the architect could select, but you got to have that discussion early on for sure.
Okay. A little kind of on a related note, your discussion about reducing the energy load and whether or not to upgrade service and those sorts of things. First part of the question is, do you account for grid cleanliness when, whether it's a clean grid or dirty grid when you're making some of those decisions?
A lot of the electrification projects that we're undertaking do, sort of look at the building, optimizing the building, because there are, the utilities have a way to go. In the district, Todd was telling me how the local utility, Pepco, was sort of very concerned about the electrical grid capacity to electrify and that then the decisions or discussions were being had about should the district be pushing for sort of decarbonization to the extent that they have been pushing. I think when we look at electrification solutions, we're always focused on our building, but if there are opportunities to use district energy in a much more efficient manner, but also in a cleaner manner, we're definitely an advocate for that. I think in the future you're going to see a lot more popularity for microgrids, where sort of neighborhoods are going to start forming these nodes, energy nodes, to supply energy, hopefully in a better, cleaner way than what the utilities and utilities are stretched in terms of what they're able to do and kind of upgrades that they're able to undertake based on financial sort of restraints. So yeah, to answer your question, we typically look at both, but in terms of influencing decisions, we always look at what the building can do given the circumstances and given the fact that every other neighbor in the neighborhood is going to have a benchmark that also relies on an energy benchmark that also relies on a grid that's not that hasn't been decarbonized.
And I'll say too, I'll just add that what you're doing and how you're looking at the cleanliness of the grid is going to be based on why you're doing this decarbonization in the first place. So Maryland and DC both have existing building energy performance standards that they're now enforcing, where buildings have to reduce their carbon emissions one way or the other. But they look at different things. So the Maryland Montgomery County BEPS program requires that you reduce your site EUI. So that's what your meters are seeing. And in that case, it doesn't really care about what the fuel composition feeding Pepco's grid is. It just wants your personal utility meter to go down. In DC, they use Energy Star score. An Energy Star score does take into account the cleanliness of your energy sources. And it looks at weather normalized source energy use intensity. And that all that means is it looks at what sort of power sources are feeding into Pepco. And Pepco is like in the whole country, it's a medium clean grid in our area. And Dominion in Virginia is similar. But we've what we've calculated, looking at what their fuel mix is for power generation, you need to, when you're implementing an electrification program, get to 2.7 times more efficient when you're taking out a on-site gas-fired system in order to start breaking even. So anything like 2.8 to, we can get coefficients of performance up to 5 or 6. Anything in that range is a good source of reducing total carbon emissions as a result of your building. So Virginia doesn't currently have any codes that require you to, for your existing building to meet a certain performance standard. It's been brought up in the past, so I don't know if it will have any legs going forward, but it is the law now in DC and Maryland.
Okay. Thank you for that clarification. Still on topic of electricity in the buildings, do you see, rather than rewiring buildings, do you see electricity over IP having any greater uptake in the industry? You
I
mentioned
think the
you mentioned wireless controls, but
Yeah, yeah. I think that's also another strategy, but I think it just hasn't taken hold. I mean, I'm sitting in an office here. Our office uses sort of the Cat 6 to the we have it's smart solutions for lighting systems that use basically 24 volts instead of to deliver light to deliver power to the light fixtures. And that also picks up your lighting controls. So these are great solutions. I think the industry as a whole has not really made a lot of headway in kind of going in that direction. But I've always said that you've got PV systems that are put on roofs of buildings, and these PV systems generate energy at 24 volts. Wouldn't it be great to overcome all of the losses, to take that 24 volt and then take it straight to your fixture? Your computer, your laptop is using this big block, and that's basically a transformer that's transforming energy from 120 volts that you're getting off the wall into your computer. Wouldn't it be great to get that 24 volt energy source directly into your laptop or your equipment where you need it, and then keep the 60 hertz and the 120 or the 208 volt for your fan systems and things that have motors in them? I think we're starting to have that discussion, and that's got a good way to go. But for historic properties, I think you've got to be a lot more careful. These light fixtures that use 24 volts are not widely available in sort of a historic setting. They're available, but they're just not sort of used for historic settings.
I, that's an important point. I'd like to take off in a slightly different direction. The things that are not readily available. On the topic of building operations and maintenance and staff training, there's a difference between institutional clients, which is many of your examples, and private clients, which may or may not have bandwidth or structures to train and retrain staff. To what degree does maintenance knowledge and systems and practices, how do you bring that discussion in with your owners, especially as evaluating first costs and ongoing costs?
Yeah, it's important to, when we're designing these systems, one of the new requirements that LEED is requiring when you do commissioning is current facilities operations and maintenance plan. So it's both a training system and a guidebook for how to drive this particular building for any of the building engineers going forward. And it really does get built in during design, especially when you're bringing on either your commissioning agent or your energy auditor to make it a deliverable from them to be able to provide that document to the building during design, so that it's built in and the contractors know what kind of training they're going to be expected to provide. And then that this is a deliverable product that the commissioning agent will train the building operators on. We have a historic building in DC where this is very thing is an issue right now. It's the historic Franklin School, which is now the Planet Word Museum. was a historic structure, and it incorporated a lot of those sustainability systems that Hala was bringing up, like VRFs. But one of the problem areas we found is that the newness of some of these VRF systems in the US leads to a shortage of qualified technicians and people able to service them. And what we had to do is make sure that we have required a service contractor to be certified in these specific Hitachi, in this case, VRF systems, because the closest service center that will service this type of system is in South Carolina. It's not really local and convenient, but having a local service provider who goes through that training down in South Carolina and that was built into the original design requirements for the mechanical contractor helps them to, like, now we have a local person under contract and on call for when these things do have an issue.
Yeah. And I would add that these are discussions, again, that you want to have, just like with the access panels, these are discussions that you want to have very early on with the client. I think there are clients that'll tell you, whether I don't want you to design these complex systems. The systems are already complex in terms of, the heat exchange between the systems where you're taking a heat from one zone, putting it in another zone. It requires a lot of sophistication on part of the operator to really understand how to operate it to its potential. But we don't want to make it too overly complicated. If the building owner is telling us, I don't have the support to the capacity to support a lot of this stuff. So I think that's definitely something that influences a design solution at the very beginning of the job. And it's a discussion, just like a discussion we're having about, constructability and system selection. Maintainability is a big part of it as well.
I really appreciated your comment about the Michigan's capital, about how the original landscape architect didn't envision a service parking lot in their plan. That relates right to your comment about neighborhood electrical systems. There's in historic and adaptive reuse, that if the envelope is fixed, it's hard to squeeze much more into that. Whether it be rated chases for VRF systems or otherwise. There's often opportunities in the landscape. On the historic preservation side of things, can you speak a little bit to how you've engaged with the historic character of landscapes, or how your clients have built community feedback for adapting landscape to, whether it be Berry transformers or any feedbacks on that kind of topic?
Yeah, we actually have we're currently designing a high profile project, a very prominent building in Washington, D.C. And typically mechanical engineers, we don't sit on NCPC and CFA meetings, but in this particular case, we were asked to kind of talk to the sort of these committees or these groups, to talk to them about where are we putting the cooling tower and how are we making efforts to really address the plume that you might see in shoulder seasons. These are things that again, that we do quite a bit of, and you gotta come at it for historic projects specifically. You gotta come at it from with an integrated mindset, that you're offering a solution. It's not just about energy efficiency and the system. Where are there opportunities to really make this building pop? And I think we all feed into that and contribute to it.
Okay. Well, we're almost done. If anybody has it's been a good conversation so far. I've got like one last question, but if anybody else has anything they want to add into the Q&A, now's your chance. All right. I think this question, I guess this was going for Todd. Building automation systems. A lot of the efficiencies, in my opinion, does kind of come down. You can't measure, you can't fix what you don't measure. And yet, first cost for BAS systems is often taken off the table in my experience for a lot of nonprofits in particular, because they know they don't have necessarily have the expertise to manage it. Um, do you have recommendations for low cost or open source BAS systems that your clients have had success with?
Um, I'm not an expert on the first costs either. And it depends on the profile of projects. You'd be surprised what it can be. We had a upgrade project that we did at Carnegie Hall a number of years ago, where they were upgrading it's a couple towers. They were upgrading one of the towers, and it was initially awarded to Schneider, and then Siemens actually came in and gave them $1 million to install the system. Because one of the ways that these controls companies look at revenue is service contracts. And what they know is if you have a Siemens system in your building, you really have to go to Siemens to get it maintained. If there's something going wrong with it that the building operators, like you say, aren't necessarily equipped to deal with, they now have like a local monopoly in that building forever. But there are more open source communications and controls protocols. Automated logic is a platform that doesn't rely on a central like Siemens, Schneider, or Johnson Controls company, but they have more of local contractors, so you can have a little bit more leverage when you're picking your providers. And that's with automated logic. I find it to be easier to train on as well. Oftentimes, Siemens and Schneider and JCI get very into just reading like lines of code, and that's how they program their systems. That's kind of how they kind of keep their monopoly on their sequences. Automated logic is more graphical and uses like blocks and symbols to simulate the programming of individual sequences of operation. So I find them just to be the most user friendly, as well as the most options for an actual service provider, and easiest to train on. I don't know anything about the initial costs comparisons.
Okay. Sounds good. Thank you. Well, I think that is the end of our questions. If there's nothing else from the crowd, Delaney, do you want to wrap us up?
Yeah, thank you so much. And great presentation, Hala and Todd. Really, really appreciate you all being with us. And thank you everyone for joining. Hope you can join us on July 23rd for our last and final session. I think that's everything. So hope you all have a great rest of your day. Take care.
Thank
Thanks,
you all.
everyone.
Thank you.
Thank you.
Bye.
Bye-bye.